Hi, everyone, and welcome to our Connected Lab webinar called Get Life Sciences Data to the Cloud. We're hosted today by Lee Tesler from AWS. Lee, I'll let you take it away.
Thanks, Simon. Many life science organizations are on a journey of lab modernization and digitalization, and many have been stuck somewhere on that journey. Maybe you have. Even companies successful in piloting connected labs have found it hard to move beyond a pilot lab up to scale. And the reason for this is an absence of a modern data strategy in these efforts that equally matches the IT tools with the scientific needs. In this webinar, we'll show you how companies are creating digital labs that can scale across an organization and provide scientists with incredibly fast speed to insights by dramatically shortening the cycle time from data generation to having data at the fingertips of scientists, data scientists, and leadership for visibility and insights and downstream analytics. To introduce myself, I'm Lee Tesler. I'm a tech strategist at AWS and a computational biologist by training. I'll be sharing how AWS is guiding companies to develop digital lab capabilities that can scale from a small startup up to large global biopharmas. I'm joined by Anish Karve, the Chief Technology Officer of Quilt Data, an AWS advanced technology partner whose company is focused on the core enablers of digital labs, including creating visibility and annotation to scientific data sets effectively, and increasing the utility of data to many users in an organization. Finally, I'm honored to be joined by our customer, Adam Mendez, Associate Director of Data Engineering and Digital Research at Resilience. Resilience is a technology-focused biomanufacturing company, and they used Quilt and AWS to go live with its 100-instrument digital lab operation, spanning 5 of their biopharma manufacturing sites. Now, their large scientific data sets are streaming to a dashboard for scientists and business users to view, to analyze, and to collaborate on, which gets updated every 2 to 5 minutes. And what's more, the Resilience platform was deployed in a matter of just a few weeks. So it's really stunning the speed at which they deployed this program and the scale that they achieved with such a small team. It's really a vision for how to build the data foundation for fully digital lab operations. So let's get started. Since 2013, AWS has helped leading life science organizations migrate to the cloud and find new ways to accelerate innovations and optimize their businesses in a secure and scalable manner. The pace of scientific innovation is incredible today, and it's your pace of innovation that's really helped us at AWS develop our roadmap to meet you where you are. Our hope is to help you take what's happening in your research labs and to help you scale it and to help you apply it further and more effectively across your organization. As far as the industry has come with R&D modernization, companies see that the job of carefully moving data from instruments to a system where they can use the data, that job takes away some of scientists' time. The job of combining data sets to harmonize data creates bottlenecks and slows the ability to get data in the hands of people who need it to get full value from the data. Researchers have more software tools than ever before, but when these software systems are disconnected from one another, it can detract from the efficient coordination of people and information and work. And for many organizations, they struggle with reducing the silos to enable secure and flexible collaboration environments to scale the partnerships that are needed. And AWS is moving quickly in this space, and we have new services, partners, and accelerators to help in the core areas of the lab. So today I'll be talking about how the AWS Digital Lab strategy is being used to make data collection automated, that enables data productization, that improves lab automation, and that optimizes your laboratory through AI and machine learning models. So we see this vision coming to life with our customers through 6 capabilities. The first starts with the instruments. A digital lab needs the right tools for collection of data from nearly any data source and the ability to do that at scale. And we can help here in the form of AWS services, reference architectures, and partners to help companies achieve that. Once data is collected, it needs to be governed. data integrity is a bedrock of science. Labs want to make sure that data is available to the right people to be able to set up collaborations, provide provenance of data assets, and ensure that the data is secure. To help here, AWS provides a unified governance approach to your lab to provide self-service access and to help you adhere to data as a product principles. And Anish is going to be going much deeper into this topic. Research is rarely linear, and oftentimes the most helpful tool is a search bar. Today, companies are deploying search applications across their lab data, including experimental results, simulation results, and materials and chemical inventories, for scientists to do things like conduct verifications and do lookbacks, for leadership to have a control tower view over the data as well. Once data is collected, it needs to be analyzed. Large-scale data processing tasks like genomics, image processing, molecular simulations require high-performance computing. And AWS has over 500 computing instance types to help. And we pair those with life science applications so that you have the right compute, storage, and networking to provide the best flexibility for your scientific workload at the best cost. On top of all the data that's collected and processed, labs are developing ML models to accelerate their science, as well as optimize their workflows by using predictive capabilities. AWS services and architectures are helping customers predict biomolecular structure, function, protein-protein interactions, and more, making disease predictions from raw health data, and so on. And finally, labs rely on electronic lab notebooks and lab information management systems, LIMS, as their central user interface for scientists to help manage samples, manage experiments, keep an eye and track reagents. And AWS has several cloud-ready LIMS partners that integrate with AWS services. And what's more is that we have low-code tools that are helping labs create integrations between lab systems to create fully integrated and automated labs. So one key tenet of this approach, when you build this, consider the journey of the data and think beyond the silos. When you consider the different roles and responsibilities in an R&D or a lab environment, like the personas that you see in green, you can consider these as different systems and people that are producing data or consuming data from this ecosystem. And when you build these different capabilities on AWS and with partners like Quilt, it allows you to create connections between these personas and enable valuable feedback loops between these systems that's connected through the cloud. So consider the journey of the data. Another tenet is you don't have to do it all at once. We're finding that companies are seeing the fastest benefit and the most impactful ROI by building a foundation based on automated data collection, data governance, and discoverability of data. These then set the stage for other capabilities that labs envision, like using HPC in the cloud for analytics, for simulations, for machine learning modeling, and full event automation. And finally, you don't have to start from scratch and you don't have to do it alone. We have a partner that spent a lot of time in this space building wet lab and dry lab data frameworks on AWS. And they have a unique and agile solution for several of these key enablers. That's, of course, Quilt Data. And with that, I'm going to pass it to Anish, CTO of Quilt, to show how Quilt can create the building blocks for connected labs in discovery, translational, clinical, and biomanufacturing. Anish, welcome.
Thanks, Lee. On this theme of this journey of the lifecycle of the data from maybe on-premise instruments to the cloud, I want to talk to you a little bit about what good looks like and where we're headed as an industry. There's actually a Nature paper written on the concept of FLAIR data, and that stands for findable, accessible, interoperable, and reusable. And I'd like to add an L to that, and that L stands for linkability. Now, the important thing about FLAIR is that this provides a descriptive goal for where we as an industry are headed and what ideal data usage and application looks like inside of your organization. I've emphasized reuse there as the last and I think the most pivotal of the 5 letters, in that reuse is where collaboration really comes to bear. And as you build up this data chain of custody from instrument to scientist to filing, you want to ensure that you can reuse and reconstruct data across people, across machines, and across time. Now, one of the issues that I think it's important to acknowledge is that this is much more than a technology problem. So FAIR is a descriptive destination, FLAIR is a descriptive destination, but it isn't a prescriptive method for how to actually apply that in your organization. And especially at scale, this feels very intimidating. So I just want to acknowledge the human side of the journey is that it's never like you flip a switch and all your data are FLAIR. This is a process. And I want to acknowledge that many teams feel frustrated by the state of their data. And I have a little acronym for that FOUL, which is fragmented, overwhelming, uncertain, and lost. And it isn't that anyone wants that as an end state for their data, but I think it's really important to acknowledge where a lot of teams feel stuck. And this FLAIR journey is a progressive and iterative journey where you apply tools from the AWS ecosystem, you apply success patterns from other partners like Resilience, and then eventually, dependent on the use case, you make the data FLAIR enough for what you need to accomplish. And this reminds me a little bit of Walt Mossberg's technology column, which launched over 20 years ago now. And what he said is personal computers are just too hard to use and it isn't your fault. And the key thing here is just to get people who are thinking about connecting their labs and having fully digital labs is that this is going to be an equal part human and technological journey. One of the things that I'd like to emphasize is that if we're going to achieve FLAIR as an industry in biopharma and manufacturing and discovery and clinical phases, we need a new mental model as an industry. And the key thing for us, and something that we have thought a lot and worked a lot about in the open source, and I'll explain why in just a moment, is that this concept of a universal data container is missing. And in biopharma, we tend to deal with very heterogeneous data. What does that mean? We may have Excel files. We have hundreds of thousands of cell images. We may have NGS, RNA-seq, single cell data. And this really spans the full gamut from structured to unstructured to semi-structured data. And this concept of a universal data container, there are 5 characteristics that we've found make these data containers or data packages, we call them, extremely useful for collaboration and reuse across the organization. And those are, I'm going to talk about each of these in detail: immutability, human readability, structure agnosticism, logical as opposed to physical organization, and finally validation. And you will recognize that word validation if you're thinking about manufacturing and you're thinking about constraints or compliance regimes like GXP. So you can, as I mentioned, these open source biopharma data containers that we're pioneering are available in the open source. You can scan that QR code or check us out on GitHub. And the importance of an open standard here is really that your data should always be your data. And that means open file formats under open source APIs, under IAM policies that you control, and all the data resides in your AWS account. So to speak a little bit about immutability, this is really a characteristic that facilitates iteration and compliance. And the surprising insight that I'd like to share here is that if you as an organization do not have an immutability and data versioning strategy, you're going to find compliance very difficult. And the reason for that is that compliance is really the process of proving that you did what you said you did when you said you did it. And immutable data in this context means that any subsequent modifications and deletions to the data have no effect on prior revisions. Why is that important? Well, science is an iterative process. And we come from an era of data lakes, data warehouses, data catalogs, where changes were very expensive. And if there was a single master for the database, and if you deleted it or modified something in an unexpected way, it could have disastrous consequences. And so immutability really provides, these immutable data collections really provide your teams with the confidence that they can branch and experiment without fear of losing their progress from the past. And the important thing to think about is that when we finally go to produce the ultimate artifact for our asset, let's say something like an IND filing, that IND filing needs to document what we call the data chain of custody from instrument to scientist to filing. And the links in this chain of custody are these immutable packages or collections that essentially represent all the evidence we use to reach the conclusion at hand. On this point of structure agnosticism, I just want to make the point that the real power of AWS services like S3 is that you can mix all levels of structure into a single collection. So we've talked about the heterogeneity of biopharma collections, FASTQs, Excels, images. And this is why blob storage got its name, is that you can put any type of data into blob storage. And then the open source Quilt libraries that I've talked about a little bit really allow you to wrap all of these assets into a single tagged and immutable unit, which is versioned for compliance. The next concept that I want you to start thinking about is there's a lot of anxiety around what I would call schema planning. And the old top-down view of the universe was that you had to kind of interview every single team and find the single comprehensive schema that worked for wet scientists, for dry scientists, for different programs, for different applications. But that is a prohibitively expensive and front-loaded process. And it particularly doesn't harmonize with discovery, where the emphasis is really on velocity of experiments. All the experiments are different because we don't know exactly what it is that we're looking for just yet. We'll know it when we find it. And so this key concept here, which I want to introduce, is that of schemas being discovered as opposed to being planned. And what I want to observe here is that top-down schema planning is expensive and it's very brittle when you bring in new instrument types and new teams. And the key point here is when you have a structure agnostic data container, you can do what we call schema hardening. And that is, you can start with very unfirm, uncertain schemas that aren't fully determined from a type standpoint or even from the definition of the different column standpoint. And you can gradually, in a bottoms up data lifecycle, going from raw data to refined data to curated data, harden those schemas and discover, instead of planning, what exactly the structures, tags, and labels are that are important for your data set and that make it accessible to the organization. One of the last characteristics I want to talk about is human readability. And if we think about modern biopharmas, we're living in an era where wet science is increasingly guided by dry science and vice versa. And if we're going to build as a community these structure agnostic, immutable data containers, they really need to be human readable. What does that mean? It means that your dry science teams are going to come at these containers perhaps from an API, but your wet scientists are going to need a graphical user interface. Your leadership is going to need a graphical user interface. And the same data, irrespective of where it lives, needs to be understandable to these kind of cross-functional teams. And we think about these, we're going to hear this concept of a data product a lot. And essentially a data product is how we take raw symbols, really, at the lowest level, which exists in places like Amazon S3, in databases, and we assemble those into these human readable data products that include data, metadata, charts, documentation, and lineage in one. And we're going to see more of this as we progress in the webinar. But on the right-hand side there, you have a little preview of what data products can look like. And I want to draw your attention to the upper left-hand side of the screenshot that's on the right there, and you're going to see the data lineage or data chain of custody. You're going to see a genome track visualization on the bottom, and it's a little bit hard to see there, but the data assets that are in this data package are included there. And users, whether they want to use APIs or they want to use a graphical user interface, can all access and understand the data, and it includes documentation. That could be in the form of PDFs, PowerPoints, Markdown files, whatever makes sense for your organization. And with that thought of data products, I'd actually like to turn this over to Adam Mendez from Resilience. And Adam is going to walk you through this very concrete journey of how Resilience started with lots of instruments across a variety of sites and was able to assemble a final solution that really shortened this time of traveling from instrument to scientists and ultimately achieving insight around that.
Awesome. So hello, everyone. I'm Adam Mendez, Associate Director of Data Engineering at Resilience, and very happy to be here today, co-presenting with Lee and Anish on Resilience's lab data management platform, and to talk about how Quilt fits into our solution. To set the context, though, on who we are as a company and the motivation for building this data management platform, Resilience is a biomanufacturing company based here in Boston that really focuses on providing the rapid stand-up of process design and manufacturing capabilities using something called the Foundry model to help enable other biopharma companies, our customers, to essentially achieve their goals of bringing their therapeutics to market. And Foundry model is something that I believe has really only been successfully demonstrated once in one other industry, being semiconductor. And in principle, it's based on building an integrated network with these highly efficient tech transfer processes that allow parts of the business to build towards these incredibly complex technical goals, but doing so starting with the design plans that the clients create. So to stick some names to it and provide some examples you might recognize, TSMC is the name of one of the most successful semiconductor companies, and their clients are the tech giants, even before they were giant. So think places like NVIDIA, Apple, Qualcomm, all of these companies that leverage microprocessors to develop their own products, but who do not make their own chips in-house. Instead, the way that this model works is that the clients will come up with the design specifications and requirements for the hardware that they want, and they will then partner with TSMC to hand over those designs so that TSMC can figure out how to build it on a pilot plant, how to actually scale it to manufacturing, and then how to produce it for those tech companies to then incorporate in the products that they bring to market. And obvious question in that would be why, right? Why would these tech companies include some third party for all of these steps? And there's essentially two answers. The first is faster R&D. Basically, without having to deal with the tech transfer yourself, it frees incredible amounts of time and resourcing to focus on just the design. And then two, it allows for companies to have an asset light model, meaning you don't have to own a manufacturing plant just to sit at the table and get off the ground with a product. And so what this really allows is for larger companies to focus instead on their differentiating technologies, while also enabling a lot of those smaller to medium-sized companies that have a great idea, but maybe don't quite have the bankroll to get it off the ground. And taking it back to resilience, the principles are the same, because resilience's goal is to become the first biomanufacturing foundry model company that focuses on producing products that enable other biopharmas centered around 5 areas: biologics, vaccines, nucleic acids, gene therapies, and cell therapies, so that they can focus on their differentiating IP. Lipid nanoparticles, plasma-derived therapies, whatever it might be. Resilience will handle the analytical development, the quality control testing, and the GMP manufacturing services, leveraging their designs so that they can focus instead on their differentiating technology, but doing it without that enormous upfront investment in these facilities and manufacturing capabilities. And to make all that possible requires not only very talented research teams, but also modern data capabilities to facilitate them internally. And that's what we're here to talk about today, because you see, resilience has existed for a little under 2 years. And in that time, we've raised over $2 billion in funding, grown to 13 sites, 1,700 people, million square foot of facility space, and labs that house over 300 instruments. And while those are all numbers that we're proud to be able to state, what they essentially introduce is a very high degree of complexity in our digital landscape. And I will call your attention to that last number there, those 300 instruments, because that is 300 physical devices in the lab that are all generating key research data that needs to be analyzed for client projects. And truthfully, data management is an area that virtually every biotech company has struggled with in the past. Fact of the matter is that manual data movement is still the way of life at most biotechs, because in many cases, lab operators will have to manually copy experiment data from the instrument computers to hard drives or file sharing tools. So they're physically walking up to the instrument before moving these key research files onto a flash drive that they now have a unique copy of, before uploading it to file sharing tool. It could be Box, could be Teams. Sometimes they email hard copies of files to their colleagues. Worst cases, I've even seen scientists simply open up a file on their laptop and then manually transcribe the results, still sometimes to paper notebooks. So it's this very broken chain of custody for moving data around, even before getting it to your analytics software. And that model doesn't work in a scalable way, because what it really causes is a complete lack of version control or auditability in these critical client project data sets, or even potentially proprietary findings. And on top of that, with this working model, there's no centralized way for teams to share data sets with each other. And that problem very often extends even beyond the lab science teams, to the point that we see it hinder software groups as well, since they then can't properly build their informatics pipelines around these unreliable, disparate data sharing tools. And I don't bring this up to cast a shadow on the mode of operating that research teams are working in. It's really just to highlight that this antiquated means of working is the way of life at most biotech companies. And that's simply due to a lack of tooling that's been provided to enable teams to do their best work. So this is where we started. Our first challenge as part of building out this next generation data management system at Resilience was really to solve the operational headaches of lab data in order to beat this convention. And so with this, there were a number of requirements we were holding ourselves to, because we knew that we needed to tailor the solutions to fit the needs of both our research scientists and our engineering teams. So on the research side, we knew that what we built needed to serve as centralized control plane for data access, with all of this key lab data uploaded automatically to eliminate that manual transcription and manual interaction. We knew that the solution needed to enable teams to be one click away from the data at all times, while providing that version control and auditability for both process data and process results. We knew that what we built needed to be versatile. It needed to scale to handle enormous variety of these disparate, even unpredictable data types going forward into the future with various instruments that we would need to bring into our labs. And it needed to provide the ability to easily integrate with other tools and applications. That's on the research side. On the engineering side, we knew that what we built also needed to be centrally managed, but more from the tech ops aspects, such that we needed to be able to provide these new connections to instruments on the fly very easily without direct access to the labs ourselves. We knew that the solution needed to scale to hundreds of instruments across dozens of sites, and we knew that what we created needed to be deployable through infrastructure as code across all of these sites and these environments. And then lastly, we wanted to really retain fine-grained access controls such that users could be declared globally by site, by team. Access can be dictated by single file, even really anywhere from these broad scopes to very specific user controls on permission for who can access what data. So a lot of requirements that meant we needed to be thoughtful in our approach. And I would say that, like any good solution, it found its roots through a few rounds of evolution. But the tech choice we arrived on for the movement of data itself into AWS was data sync. And the approach here was that for version 1 of the implementation, we leveraged AWS data sync agents hosted on-prem as VMs at each of our sites. And on each of those agents, we're capable of defining tasks that map one-to-one with instrument folders that we want to transfer that have SMB shares over the network. So source location are SMB shares, 1 per instrument, target locations S3. And with these tasks running on these distributed agents, we can start to move that data into AWS where we can store it, archive it, but also better organize it and start to make better sense of it before putting it into the hands of our end users for them to interpret. That leads into the right-hand side of the diagram you're looking at here, where we use what I'd say is AWS recommended design for data lake architectures, but with a resilient spin on it for 4 bucket tier strategy. And in essence, this is a way for us to land the data and then take it through a maturity curve, flowing left to right and then top to bottom, such that we can follow precise naming conventions to organize the data by prefix, while also performing any transformations we need that make it more digestible or partition it so it's more queryable. So a lot of thought going into the organization of the data and the ingestion mechanism, but the work wasn't done there because, like I said, every good solution exists through iteration. So a few things to consider with data sync. The first is that data sync operates normally on a schedule, and that scheduling only supports a maximum task interval of once per hour per task. So data doesn't always move immediately because these tasks are mapped on agents that have no knowledge of the lab devices themselves. They simply move the data at an interval of once per hour per task. And that represents some challenges because it means that we're ultimately slowing down the turnaround time on getting those results into the hands of scientists. The other challenge is that not every instrument generates data at the same rate. So we were finding that some of the task executions that get queued wouldn't actually do anything. Sometimes the task would spin up, see that there's no data to move, and spin back down. That whole process only wastes about 4 to 5 minutes per task. But when you consider the fact that we're looking at dozens of instruments, that means you're building up a backlog of queued data that's not moving because it's waiting for these empty tasks in front of it. And that's really just farther extending the turnaround time on getting data to users. So the work wasn't done. We knew basically that we had to optimize the system to bring down the turnaround time on moving that data into AWS to make it more on demand. And so the next iteration of the solution was to create the concept of smart devices out of each of our lab instruments, such that we could monitor in real time the changes to data generated on the instruments and be confident that we would only trigger the data sync tasks at the time new data appeared. So right-hand side of the diagram is still the same, but what changed is the logic to trigger tasks such that we no longer needed to operate on that schedule. And double-clicking on the smart device analogy, the way that this new setup works is actually leveraging AWS IoT, Internet of Things, to run greengrass agents that are capable of monitoring those same shares that the data sync agents are transferring from. Those greengrass agents run edge compute, edge lambdas, which can see the last modified timestamps on the lab devices. And then what they do is compare that to a global lookup table in DynamoDB to see if anything's changed. If the timestamp in Dynamo is newer, we know we're up to date, no new data has appeared, nothing happens. But if the timestamp on the instruments is newer, we know we have new data. And so we use that to fire the execution of the data sync task. And this solved a lot of problems because it means that not only do we no longer have to wait for that arbitrary 1 hour marker before we kickstart any migration task, but it also eliminates the unnecessary running of tasks that don't have any data to move, since we're confident that we'll only start the tasks whenever the Greengrass agent sees new data appearing on the lab device. And so the result of this is that we were able to hit the mark on those final requirements that we were looking to build. Now, to stick some numbers to it, what this means is that we've been able to, in the span of just a little over a month and a half, create this global system for data ingestion and get over 100 instruments across 6 sites connected and all channeling their data into AWS such that data will land in S3 just 5 minutes from the time it's generated on the lab devices. And to touch on the infrastructure as code piece one more time, because it's these reusable code snippets to create new connections with new devices, onboarding more instruments is quick for our team, to the point that our current record is 22 instruments in a day. That was actually at one of our San Diego sites where we migrated the entire site in the span of just 3 days. So this whole setup solves a number of problems. It's really that set of hurdles that we mentioned in the previous few slides, in that we now have a way to eliminate manual data transfer and transcription. We can provide that centralized means of data backup. We can get data to the scientists faster to speed up learning cycles. And we can really begin to enable some of the more advanced automation that we wanted to provide. But all of this was really just the setup for the next challenge, which was how do we front end this to users in an intuitive, easy to use way, but without compromising on the engineering efforts up until this point to really place that emphasis on data integrity, immutability, reliability. And for that, we turned to Quilt. So first and foremost, Quilt is a search interface into S3 that scientists understand, because it's leveraging the well-structured specific organization we've built for each of the instruments, where users know exactly how to navigate to the data that's generated on each of the devices. That's the second screenshot you're seeing here on the right, with data laid out by organization, site, and instrument, with very wide range of bioreactors, flow cytometers, sequencers, digital PCRs, such that users can simply click in and see their data. But Quilt also provides a search bar, and it's very much like a Google search, where you can look through the millions of files we have in S3 that are rank sorted by the hits they receive. So you can search by specific names of the files if you know them. Could be by instrument, could be by date they were created, type of file. It's very wide range in terms of search options that really makes it easy for our scientists to find the data uploaded to AWS. And when you find what you want, you can visualize it, oftentimes inline within the browser. What we happen to be looking at here is a microscopy image for nuclei stains on a tissue section. And from there, you can simply download it. There's a button up at the top to do that, but you can also retrieve it programmatically, because for every file here, you'll see that Quilt actually auto-generates a code snippet that tells you how to retrieve it directly from AWS to develop your informatics pipelines around. Second most important feature of S3 that Quilt leverages, and Anish mentioned, is that it allows scientists to leverage S3 data object versioning, because Quilt gives you a view into every historical version of a file that's ever existed. That's this drop down here with hash IDs, where every version of that S3 object becomes an immutable link with these point in time restores that I can always jump back to. And if you think about it, this is pretty critical for many of the data integrity aspects, because mistakes happen. Maybe a lab operator deletes or accidentally overwrites some raw experiment data on the instrument itself. But with this versioning and historical linking, you know that you're always going to have safe copies here that are immutable. You could quite literally never accidentally delete or ruin your data. It's just not going to be possible, because it simply becomes a new object version. So in that sense, Quilt and this data ingestion process we've built is also serving a lot of the SDMS functionality for capturing data changes and archiving the data generated by each of the lab instruments. And then the last piece I'll mention are Quilt packages. Anish spoke a bit about this, but simply put, packages act as something akin to Git control for data sets, where users can consolidate both the processed and raw results under this single URL that's version controlled and one link accessible the same way that files are. But also, users can add metadata tags and commit messages that become searchable. So it really encourages users to annotate their results and describe what are the changes they're making while giving a means for other teams to easily find their reports. And I'll give you two tangible examples of how we at Resilience are using this now. The first is that we're able to provide these searchable grouped analysis results that are the output of many of the informatics pipelines we have running. Essentially, data lands in S3 via the data sync IoT setup we talked about, and then a simple event kickstarts our analysis pipelines, which can then publish those process results back into S3 as a Quilt package. But it can do so with all of the metadata that describes all the configuration parameters that went into the job, essentially making it this incredibly efficient process for providing process results to lab teams. Our second biggest use case is for linking datasets to ELNs. And for those that don't know, ELN is an acronym, stands for Electronic Lab Notebook, which are these virtual tools that scientists use to provide annotations and interpretations of experiment results. But what they very often lack are easy associations to the raw data. Very often scientists will just manually transcribe data points or upload hard copies of the results to those ELNs. But now that we have all the data in one centralized place with the raw instrument data and the analysis results under one Quilt package, we can simply insert that link into the package into our ELN entries instead of uploading those hard copies or manually transcribing results. And that link behind the scenes can point to dozens and dozens of files or even terabytes of data in S3, but it's this incredibly compact link that really gives you all the auditability you need for the purpose of your IND filings or regulatory reports. So for all the reasons we've talked about, it was a very intentional choice in partnering with Quilt because it's a scientist and developer-centric tool set that essentially lets us leverage the built-in features of AWS while acting as the search engine to our IoT data ingestion process. So as Resilience's manufacturing footprint continues to grow across more sites, more key research devices, we fully intend to continue scaling our data ingestion system with Quilt acting as the front end and data engine for all of it. I know we're short on time, so I will stop here. I believe we're going to open up for questions, but I would be remiss if I didn't show one last slide just highlighting the team that contributed to building these efforts. So I'll hand it back over to you.
Thank you, Adam. Thanks, Anish. If you could both come back on video now. Let's open this up as a roundtable discussion. Adam, it was great to hear how you've weaved or woven the Quilt technology with AWS technology for Resilience as a next generation biopharma foundry. I'll start with you, Adam. Incredible presentation. One thing I was really interested in is the operational excellence aspect of your design. You mentioned being able to extend up to 22 instruments in a day. One, how large do you see this system becoming? That's one question. And then also, can you give us a view of kind of the management and operations management of this? What's the size of your team? What's the makeup of your team that's going to be supporting this?
Yeah, absolutely. So I'll start with the team. It's a small team, small footprint of digital engineers, AWS engineers working to build this. The initial design implementation was built by a handful of just 3 of our engineers. At this point, now that we're thinking about scaling to more sites, more data, we're obviously needing to extend the support team such that we can really provide operational excellence around the turnaround time for onboarding new devices. And we see requests coming in every day from our San Diego sites, from our Boston site. People are very keen and excited to use this new system. So we're actually going through the process right now, providing a user-driven form for requesting the onboarding of new devices to help scale with the demand and the want to include new instruments. As far as the future of the implementation, like I said, it's more sites and more data, but also really building automation with analytics workflows. So a lot of the commonplace pipelines taking place coming out of the lab, image segmentation, next flow for genomics data processing, bioreactor trend predictions. The goal is to have all these pipelines publishing Quilt packages for analytics automatically. And like I said, all those processes can be event-driven, meaning that from the time raw data hits S3 through this data sync IoT setup, we can kickstart those jobs, and a few minutes later, the process results can be waiting in the form of a Quilt package for scientists.
Incredible. Thank you, Adam.
Lee, I've got a question for you, and I think it's really about business value. And one of the things I think, kind of the hidden word and the devil's in the details, is really cross-functional. And so a lot of times you'll have R&D IT, and they really have a vision for how they want data to get off of instruments, to land at the cloud, and then to be FLAIR and accessible to the rest of the organization. But they may struggle to convince C-suite that data management is a worthwhile investment. And I'm wondering, what are some of the business benefits that people in IT, operations, and engineering can highlight, so that the rest of the organization feels like, hey, this investment is going to have a return for us as a business?
It's a great question, Anish. So I speak with a lot of life science laboratories and leadership around these digital transformation programs, and I'm seeing digital transformation in the lab being driven by two main business factors. The first is the need to accelerate science. That's the ability to discover and develop new and more effective and safer medicines and therapies and bring them to patients faster than we do today. The second business driver is cost and the need to develop new therapies or carry out diagnostics or manufacture new drugs in a way that's lower cost and more productive. And so, why we can really impact this today and make an impact on both of these business factors is we're at this inflection point where cloud technology and services around data, many of the architectures that we've had that are now tested and tried and at scale, at resilience, and partners like Quilt that are making all of these things easier. And what's taken months in the past is now being done in weeks by small teams, as Adam was talking about. So the ROI equation is becoming much, much more compelling. And Connected Lab used to be about setting up a single workflow. Now it's about digitalizing all R&D data in an organization. So those are some of the things that I think about. I'll take the next one. Maybe bat this back to Adam. What advice would you give to teams at other companies who are trying to implement this type of solution? Where should teams focus first?
Yeah, it's a great question. I would say make sure that your network and data engineering teams are joined at the hip. I think that one of the most challenging parts of building any data migration system is really doing it in a secure way, which requires very strong networking and infrastructure teams to configure the lab network in a way that enables the data engineering teams, but also keeps the site safe and secure.
There's a follow-on question I'd like to ask on that, Adam. And then a lot of, especially in the middle of the market, so what we would call startups that have on the order of $100 million in funding, it's hard for them to find these large teams. And so I'm wondering if there are any resources in the AWS ecosystem where smaller teams like a lot of the teams that use Quilt are sometimes single person IT shops. And so I'm wondering if you could tell us a little bit about ways that smaller teams can think big and maybe lean on the AWS ecosystem, lean on the vendor ecosystem to get some pre-made components for their solutions, or other tips that you have.
Yeah, actually, I'll answer that in a couple of different ways. I think that you kind of touched on it around biotechs, and many startups are really looking for third-party solutions that allow them to get off the ground faster without having to build it all themselves. What we found, at least in kind of our initial evaluation, is a lot of times those third-party solutions are prohibitively cost expensive because they involve spinning up major infrastructure, major systems in some other third-party accounts that you don't have direct access to. And that presents its own set of problems because it makes it hard to actually build any of these informatics pipelines off of these kind of obfuscated environments that you don't have access to. That was actually, to kind of bring it back to Quilt, one of the major advantages that we saw in partnering with you guys was making sure that we retained total autonomy, total control over the access that we had, and being able to do it in our own sandbox environment. So advice I'd give to startups that are really looking to do the same, especially if it's a small team, is make sure you're not forced to build an environment you don't have total freedom and control over.
I've got a question for Lee. Oh yeah, go ahead, Adam.
I was going to say, actually, I had a question for Lee as well. Lee, I was going to ask, what you talk to a lot of customers. What do you often see connected labs looking like on the horizon as far as vision for a lot of the biotech companies you talk to, anywhere from 5 to 10 years from now?
Mm-hmm. Yeah, well, wow. Well, 5 to 10 years. Well, making predictions on technology can be a fraught path, but I'll give you my take on it. I see three exciting sort of threads growing right now. One is the story that we just heard, and it's the ability for all of lab data, and by extension of that, all of factory data and shop floor data and clinical data being stored as data products with discoverability and findability, no matter where they were generated in an organization. It's going to make it easier to get full value of the data, come up with new and unexpected use cases for data, and through federated access, providing the ability for different organizations to collaborate in a secure way that's privacy preserving. So bringing data in new ways and opening that data to meta-analysis and so forth. That's one trend. The other I see is the application of AI models to that data once it's been organized. I imagine it's not going to be long before companies are training and tuning large language models on biomedical data sets, then going out and asking those models to help generate a target strategy, develop a candidate strategy, synthesis strategy. So it's very hard to predict what's happening on that kind of timeline with such a fast moving area. I think AI is in there though. And then another dimension I see is the greater use of event-driven microservices for deploying automation. If you want to create a workflow notification system, you no longer need to manage servers, and you no longer need to develop a full new application and deploy it around the world. You can have a cloud engineer, a junior cloud engineer, do that with a Lambda function today. And so the ecosystem of scientific software makers is really modernizing rapidly, and they're using event-driven architectures to create orchestrations and choreography. And I think that's just going to become more and more prevalent in the life sciences. It's going to become easier and easier. Great question.
Any parting thoughts or burning brilliant insights from the panel?
Thank you to the Quilt team. Thank you to AWS team for hosting us here. Very excited to join and to talk about some of the solutions we built.
Yeah, one thought I would like to leave teams with is really this crawl, walk, run philosophy. So we've talked about a full gamut of architectural solutions, headcount solutions. And I think one of the really powerful things about being a cloud native company or transitioning to be a cloud native company is that very small teams, even single individuals, can make a big difference. And I would just emphasize this aspect that FLAIR is a progressive journey. And what that means is the first step really is landing the data in S3, getting into the cloud. And once your data is adjacent to compute, that's really the big change the cloud brings in, is the data is adjacent to compute now. When your data is near every possible service that you could conceive, the potential of what you can do and how fast you can do it really grows. So I would encourage teams not to focus on maybe an overambitious end state, but to really focus on first landing the data into S3, and then they'll find that they have a lot of options for reorganizing and distributing the data as data products to the rest of the company.
You know, I'd like to add one thing on, how companies can get started quicker, what type of support they can get from the community. So one benefit of the approach that was just described is you don't have to start from scratch. We've learned some organizations want to build, customize from the ground up and build things out of the box, while others want to more purchase things out of the box. For our builders, AWS is going to continue to offer the most functionality with 200 fully featured services available. But as you move to customers who want to get capabilities out of the box, we're providing more and more life sciences reference architectures and easily deployable guidance that are there to solve some of these core digital lab use cases, like instrument data ingestion. And then customers who really want to bring solutions out of the box and really get started the quickest, partners like Quilt offer out of the box solutions that can be readily deployed. And then for companies who are looking to leverage a consulting partner to have hands-on keyboards, we have a team of validated consulting partners that specialize in implementing these workloads as well.
Thanks, everyone. It's been fun. And we're looking forward to seeing what you do in your journey, getting instrument data into the cloud and then to the hands of scientists.
Thank you.
It's been an enlightening call. Thanks for joining, everybody.